Hi, my name is Neil Dupuganti and I will be presenting the fifth lab we performed for Physics 2212, which covered Faraday's Law. To introduce the lab, time-varying magnetic fields induce currents in other objects it interacts with. These induced currents also produce a magnetic field and force in such a manner that repels the change in the source magnetic field. The purpose of this lab is to use a bar magnet and aluminum foil as a conductive tube to better visualize and understand Faraday's Law through experimentation and computational models. In this lab, the magnetic bar fell through free space in 0.271 seconds. In the experiment, the magnet fell through the tube in 1.064 seconds compared to 0.833 seconds in the computational model. In this presentation, I will cover the fundamental principles of this lab, the experimentation and computational parts of this lab, and I will answer the additional questions with a conclusion. The main fundamental principle of this lab is Faraday's Law, which states that non-constant magnetic fields induce currents in surrounding objects, such as coils or wires. The induced current produces a magnetic field in such a way to maintain the source magnetic field. Another important principle is the Biot-Savart law, which states that currents produce a magnetic field. Lastly, Newton's laws are important for the coding section of this lab. Newton's third law states that every action produces an equal and opposite reaction, and Newton's second law states that a net force accelerates an object and causes a change in motion. In the experimental section of this lab, a bar magnet was dropped through a conductive aluminum foil tube and timed using video scrubbing software. A ferrous tube such as a steel pipe could not be used because it is magnetic, which would disrupt the falling bar magnet. 5 trials were conducted and the following times were yielded, averaging a fall time in the tube of 1.064 seconds. The magnet fell in free space at a time of 0.271 seconds. The conductive tube obviously slowed down the fall time of the magnet by nearly a factor of 5 times. The experiment was modeled through a computational model that allowed us to better visualize the magnetic field source and induced current. The point dipole acts as the bar magnet and the layer of conductive rings acts as the conductive tube. The computationally derived fall-through time of the magnet is calculated and can be compared with the experimental average time. One first highlight of the code includes setting the initial conditions, where I input the length, width, and inner radius of the aluminum foil tube, and I put in the mass and magnetic dipole moment of the bar magnet. The second major code highlight was calculating the magnetic field, where I used the Biot-Savart equation of a dipole. Thirdly, I calculated the magnetic flux rate of change by determining the proper distance and setting proper numerator and denominator equations to represent the change in magnetic flux of each ring of the tube. The fourth major step of the computational model was calculating the induced current in each ring with Faraday's law. Simply coded, the induced current was equal to the change in flux over the radius of the ring. Then in steps 5 and 6, I calculated the magnetic force on each ring with Biot-Savart's law, and I calculated the force on the falling magnet by the tube with Newton's third law. I set the magnetic field at each ring equal to the previous expression created for the magnetic field due to a dipole. Then I found B hat by dividing the magnetic field at the ring by its magnitude. I then found the sine and theta using the cross product function between mu hat and B hat. Finally, the magnitude of the force could be calculated. In part 7 of the code, the net force was calculated by adding the gravitational force and the magnetic force. In part 8, the changing position and velocity of the magnet was calculated using Newton's second law. The video graphic on the next slide will show the final result of the computational model. This slide shows the computational model results. The moving blue induced current is visible through the tube as the magnet falls. The graph of the velocity versus time is plotted as the magnet falls through the tube, and the magnet falls through the tube in 0.833 seconds. As viewed from above, the blue coloring on the tube indicates current flowing in the counterclockwise direction, while the red indicates current flowing in the clockwise direction. The magnet moves downwards through the tube, so the change in magnetic flux increases in the negative y direction. A counterclockwise current would resist the change in magnetic flux and is represented by the blue color. When you flip the magnet around, the magnet still moves downwards, but the changing magnetic flux decreases in the negative y direction. Therefore, due to Lenz's law, the induced current would be clockwise. The total time in tube with the real-world system was 1.064 seconds compared to 0.833 seconds in the computational model. The computational system could be made more accurate by possibly accounting for air resistance. The shape of the velocity versus time plot indicates that the forces become equal and opposite in magnitude, so the total net force becomes 0. As a result, the bar magnet reaches a constant terminal velocity and stops accelerating. To answer the additional questions, if the resistivity of the conductor were reduced to 0, the current induced would be much larger due to Ohm's law. The magnet would take even more time to fall through the tube. If holes or slots were cut into the tube, the model would have less rings representing the tube. There would be less total induced current and less magnetic force, so the magnet would fall through the tube faster. Overall, this lab allowed us to experimentally and computationally visualize Faraday's law. We were able to witness and validate our knowledge on the effect of changing magnetic flux on induced current.